Okay, let's finish chapter 6. The last section is 6-4, which is systems of linear inequalities and what we call linear programming. But before we go any further, let's just review how to graph inequalities. So let's say we have an example that looks like this: negative x plus 2y less than or equal to 2. And we want to graph this. So we want to put it in slope-intercept form, if you guys recall from chapter 1. So I'm going to solve this for y. So I'm going to add x to both sides. So I'm going to get this. And then since 2 is being multiplied by y, I'm going to divide by 2. And y is less than or equal, I can write this as 1/2 of x plus 1. 2 over 2 is 1. Remember, the only difference between inequalities and equations in solving them is when you multiply or divide an inequality, you got to flip the inequality sign. That didn't happen here. And then the y-intercept is a positive 1. And then the slope is 1/2, so you go rise is 1, run is 2. So you go up 1, 2 to the right. Now, this is less than or equal. So the moment you see that equal sign is a solid line, not a dash line. So remember, if you just had these signs, less than or greater than, the line would be dashed. If you have these, then it would be solid. All right, and then read the statement. Y is less than or equal. When you hear yourself saying less than, you highlight below. Now, what does that mean? That means if you pick any point in this area, which technically goes to infinity, it will satisfy this inequality. Let's say I pick 0, 0, which is in this shaded area. So if I pick 0, 0, y is 0, x is 0, do I get a true statement? So I get 0 less than 1/2 times 0 is 0, 0 plus 1. What is 0 plus 1? That's 1. Is 0 less than or equal to 1? Yes. So we satisfied the inequality. So this area, if you choose any point in this area, it will satisfy the inequality. Therefore, this area is called the solution region. The solution region. You can also have system of inequalities, such as this. If I give you 2x plus y greater or equal to 4, x minus y less than 2, here's your system. Now, the only way usually that we solve system of inequalities is by graphing, not by substitution or elimination, any of those algebraic methods. So this is inequality 1, inequality 2. Let's put them in slope-intercept form. So number 1, all I have to do is, actually let me cross that out, subtract 2x, and I get negative 2x plus 4. Over here in number 2, I can subtract x, and then I have a negative 1 being multiplied by y, so I'm going to divide everything by a negative 1. Since I'm dividing by a negative number, remember when you divide or multiply by a negative number, you flip the inequality sign. So y is greater than, negative over negative is positive, positive over negative is negative. So these are my two inequalities. So I'm going to graph them on the same coordinate plane. So the first one is 1, 2, 3, 4. That's my y-intercept, positive 4. Slope is negative 2 over 1. So from this point, I come 1, 2, 1, 2, and 1. This is greater or equal to, so it's a solid line. And you see y is greater than, so I'm going to shade above the line. Okay, let me use a pencil for a second one. The y-intercept for the second one is negative 2. So I'm going to, and the slope is 1 over 1. So I'm going to go up 1 unit to the right. It's just greater than. So it's a dashed line, and y is greater than, so you shade above the line. So where the two shaded regions overlap, that will be the solution region for this system of inequalities. That means if you pick any point on this line, I'm sorry, in this area, including this portion of this line, because it's solid, not this line because that's dashed, so not on this line, but any point in this region, it will satisfy both inequalities. So that's the solution region. Okay, let me do one more example. I was going to do example number 4 on page 545. Example number 4 on page 545. It's about investment planning. But the so if you read the problem and you see the way it's set up, I'm sorry, I can't talk anymore. The way the inequalities are set up, it will show you how you set it up. So let me show you. And it says, as a part of their retirement planning, James and Lily decide to invest up to $30,000 in 2 separate investment vehicles. First is a bond issuing 5%, and the second is a money market certificate paying 3%. A financial advisor suggests they invest at least $10,000. What does that word mean, at least? That means either 10,000 or more than 10,000 in the certificate and not more than 15,000 in the bonds. So the bonds is just 15,000 or less. So take a look at these inequalities. They have $30,000 to invest, so they either investing them in the bonds or certificates. So add those up, it's either 30,000 or less than. That's all they have. Bonds should not be more than 15,000, so they can be 15,000 or more. And certificates should be at least 10,000, so 10,000 or more. And it says bonds cannot equal to, bonds can be either 0 or greater than 0, obviously. I would have, so bonds cannot be less than 0. And obviously certificates cannot be less than 0 because otherwise you have no money invested. So how do you graph these? So if I have B plus C greater than, less than or equal to 30, and B is less than or equal to 15, and C is greater or equal to 10, and B is greater or equal to 0, because it's less than or equal to 15, but it can't be less than 0. You don't have negative numbers. Okay, you can pick one of them to be your X, your horizontal, and one of them to be your Y, your vertical axis. And since we're dealing with money, everything is in the first quadrant. Everything is positive. So I'm just going to draw the first quadrant. And let's say this is your B, and this is your C, bonds and certificate. And bonds can not be more than 15. So let's say you are going by 5s. So 5, 10, 15, 20, 25, so forth. And let's say we go by 10s for certificates, or we go by 5s. 5, 10, 15, 20, 25. Now I'm doing it by hand. Again, it's not very accurate, but if you have graph paper, it makes a big deal. Okay, so let's graph this one first. X, if your B is horizontal, so it's acting like X. So X is less than or equal to 15. So that's a vertical line at 15, and it's a solid line. So you go, if I can draw a straight line, you like that. And it's less than or equal to 15, so you shade to the left. This one it's your y, c is acting like your y is vertical, so y greater or equal to 10 is a horizontal line, and it's solid because of that. Go that way, and it's greater than, so you shade above. So far here. And this one, since c is your y, or acting like y, let's solve for c. So you get c less than or equal negative b plus 30. So now that's in slope-intercept form, right? So your y-intercept is 30. Your slope is negative 1 over 1. So you come down 1 unit to the right, something like that. It's a solid line. Again, my graph is not the best. Something like that. So, and it's less than, so you're going to shade here. So therefore, this is my solution region, and it's bounded because it's, you see, it's obviously bounded by these four sides. I have a little trapezoid looking figure here. So it's bounded. If one side was open and you could have continued to infinity, it would be called unbounded. And these are called corner points. So basically this couple, if they pick any point in this area, it will satisfy the constraints of what they have for the investment. So for example, they can pick, let's say, this point, putting it right here, 10,000 for bonds and 15,000 for certificates. That's within this region, and it does not exceed their total. Okay, or they can pick 5,000 for bonds and 25,000 for certificate, something like that. So as long as they pick in that area, that would be the solution region, and it will satisfy the inequality. Okay. Now, let's talk about linear programming. What is linear programming? Excuse me. If you look at the bottom of page 546, the description is there. It says, to become profitable as possible, corporations look for ways to maximize their revenue and minimize their cost while keeping up with delivery schedules and product demand. To operate at peak efficiency, plant managers must find ways to maximize productivity while considering employee welfare, union agreements, and other factors. Problems where the goal is to maximize or minimize the value of a given quantity under certain constraints or restrictions are called programming problems. The quantity we seek to maximize or minimize is called the objective function. For situations where linear programming is used, the objective function is given as a linear function in two variables and is denoted usually by f of x, y. So you have linear programming. Sometimes you don't have linear programming, but for the purposes of this class, it will be linear programming. A function in two variables is evaluated in much the same way as a single variable, so you just plug in the values of x and y over there. And on the next page, here, it says when objective is stated as a linear function in two variables and the constraints are expressed as a system of linear inequalities, we have what we call linear programming problem. The system of inequalities solved, like the example we just did earlier, produce solution regions that are either bounded, like I explained, or unbounded. And anyways, once you graph the inequalities, under these conditions can be shown that the maximum or minimum values must occur at one of the corner points of the solution region, which is also called the feasible region. So I would like to do an example, which is a little bit long, but it's important. Example 8 on page 549. Okay, so let's do this one together. I hope you guys can see it. So it says the owner of a snack food business wants to create 2 nut mixes for the holiday season. The regular mix will have 14 ounces of peanuts and 4 ounces of cashews, while the deluxe mix will have 12 ounces of peanuts and 4 ounces of cashews. The owner estimates he will make a profit of $3 on the regular mixes and $4 on the deluxe mixes. How many of each should be made in order to maximize profit if only 840 ounces of peanuts and 348 ounces of cashews are available? Now, there's a whole lot of information in this problem. That's why when you encounter these type of problems, it is best to visualize it for yourself. So that's why this table over here. So let's see how they set up the table. It says our objective is to maximize the profit, and the decision variable could be R to represent the number of regular mixes sold, and D for the number of deluxe mixes. So you have the deluxe mix and you have a regular mix. So you can pick X and Y, but this problem chose R and D to make it easier to figure out which variable represents what. This is your objective function right here. Underline it. This is your objective function. You see P, you can use F, whatever, but P for profit, regular mixes, deluxe mixes, and where do we get 3R? The owner estimates he will make a profit of $3 on regular mixes and $4 on deluxe mixes. So this is your profit equation, which you want to, or your objective function, which you want to maximize. All right, the information is organized in this table, and let's look at it. Okay, so these are the weights of peanuts and cashews that you have, and these are the numbers. You can also put the weights up here and put the numbers down there. That doesn't matter. Okay, so ounces of peanuts. The maximum weight of peanuts is 840 ounces, right? That's given to you, 840 ounces. And the maximum amount or weight of cashews is 348. That's where we get that number from. Okay, now it says the regular mix will have 14 ounces of peanuts. The regular mix will have 14 ounces. Okay, 14 ounces of peanuts and 4 ounces of cashews. You see, 14 ounces of peanuts, 4 ounces of cashews. That's for regular mixes. Okay, and the profit for that mix is $3. Just the whole information that's given to you in this problem, it's organized in this table, so it makes it much easier to recognize what's going on. The deluxe will have 12 ounces of peanuts and 6 ounces of cashews, and the profit to be made from that mix is $4. So here we go. All right, so now how do we come up with the equations, or rather inequalities? Very simple. 14, this is the number, 14R plus 12R. These are the weights, sorry, these are the weights. So R is the number of regular mixes. So 14R, because every regular mix will have 14 ounces of peanuts and 12 ounces of cashews. So you're basically going horizontally here. Should be equal or less than 840 ounces. So the weight of the peanuts for both mixes cannot exceed 840 because that's all the peanuts you have. Now you can go this way for the cashews. 4R plus 60 should equal or be less than 348. That's all you have. Now R and D both have to be greater or equal to 0, because if it's less than 0, you don't have any regular mixes, you don't have any deluxe mixes. Okay, so these are your constraints. All right, so then again, just like that problem, we can pick the D to act as Y's and pick the R act as our X's, and solve these for D's, put them in slope-intercept form. So basically you move the 14R to the right side. I'm just going to do one of them. right? And then divide by 12, and then graph it. And you do the same thing with this one, and then graph it. Now, since we're dealing with weights, everything is positive. We cannot have negative weights. That's why everything, again, is in the first quadrant, okay? So let's take a look at the graph. R is the horizontal axis, and look at it, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then, because if you divide 840 by 12, let's see, 840 divided by 12, that gives you 70. Okay, and that's your y-intercept. So that's the graph of the first inequality, you see? And the slope is negative. You reduce this to 7 over 6. So you come down 7 units and 6 units to the right, and then you graph it. You have a negative slope. And then this one, 348 divided by 6, 58. And that's the y-intercept for this one. It's not exactly at 60. So that's the other one, okay? And they're both less than or equal, so it's you highlight below, and where they overlap is your solution or feasible region, and it happens that they overlap right here. So the first one, you like this. I'm sorry, the first one is this way, the second one is this way. They overlap in this feasible region. And these corner points, 0, 0, where it intersects the horizontal axis, where it intersects the vertical axis, and obviously where they intersect together, those two lines, those constitute the corner points of your feasible region. Now, the corner points then, they're listed in this table. Notice? So you have 0, 0, that's right there. You have 60 and 0 right there. You have 0 and 58, that's there. And then this point, if you do it on graph paper, you will know it's 24 and 42. Now you want to know which one of these points will maximize this objective function. That means if you plug these points inside this equation, which one will give you the highest p-value? Well, that will be your maximum profit, right? So if you put 0, 0, obviously you're not going to make any profit. If you put 60, 0, so 60 in place of R, 0 in place of P, you make D, sorry, you make 180. 0 in place of R, 58 in place of D, you make 232. If you put 24 and 42, you get 240. So this is the highest p-value. So that means this point will maximize your objective function and will give you the highest profit. So what does that mean? That 24 is representing your R, right? So this is your R, this is your D. So that means the maximum profit of $240 is made if you make 24 of the regular mixes and 42, it's this point, and 42 of the deluxe mixes, then you make the highest profit possible. So this is called a linear programming problem. Now, I'm not going to give you too many of them, and on the quiz, obviously, it's not going to be as extensive as this one. But I just wanted to give you one of these and to make hopefully more understandable. I recommend you definitely read page 548 and definitely look at example 7 on page 547 as well before you take a look at this example again, example 8. Okay, so we are done with chapter 6, and hopefully we'll talk and see each other on Tuesday. Take care. Bye-bye.